Okay, this lecture we're going to start on beam column element loads. Okay. This is section 5, page 5.1. Okay. And what I will do, I'll cover two things. I'll cover distributed vertical load. Okay. What I mean by this, right, is if you have an element, and we're going to orient everything into a local coordinate system. Okay, x and y here. Okay. The element will have its usual properties, right, coming from the properties of the structure, EA, I, and L. Okay. And will be subjected to distributed loading. I'm going to cover the vertical case because the horizontal case we already covered in the case of the truss. Okay, then we'll put everything together. Okay. The other load I'm going to cover is, again, we'll do the temperature differential. Okay. And what we're going to consider here, right, is, again, if this is our element, okay, E, A, I, L, also alpha, right? Remember the coefficient of thermal expansion. We're going to apply 3 temperatures here, okay? Delta T centroid, okay, is the temperature applied in the middle, okay. Delta T top, temperature applied at the top, and delta T bottom. Okay. Delta T centroid will end up governing the amount of expansion or contraction of the structural member. Delta T top and delta T bottom, okay, the various the combinations will basically govern the amount of curvature that the element develops, okay, and as you know, curvatures will then lead to moments. So this is what I'll focus on in this lecture. Okay, we're just gonna look at the element and describe the loads, and the following lecture we're actually gonna do an application. And I think that will wrap up sort of the static part of the course, and I'll get started on the dynamics. There are no notes for dynamics in the reader, and so I prepared my own. I'll upload those, and then we'll go through that. Okay. All right. So back to distributed loading. And here, again, depending on the load, you're going to get a corresponding solution. Okay, and so here I'm going to cover the case of uniformly distributed load. Okay. All right, so what we'll do here is as follows. We take our element, ij, right? We'll embed it into a local coordinate system. Again, right? Loads are modeled in the local, sometimes basic coordinate system. Distributed loads are done in the local. In fact, for the temperature changes, I'll show you the derivation based on the basic coordinate system. Right? And so assume that there's a load y, right? W sub y as a function of x. And we'll assume it's minus w, okay, constant. So we have a load that looks like this. Okay. And W has units of force per unit length. Okay. Now, for the purposes of our derivation, right, remember that the loads are modeled as follows. We'll think of the element force vector, right? It's decomposed into the element matrix in a local coordinate system times the generalized displacements, right, plus f prime f. Okay, and so in a way, right, the effects of the stiffness and the effects of the distributed loading are considered separately, right? And so as a result, right, when we consider the effects of distributed loads, we have to set this guy to 0, okay? Which is the same as going and cantilevering node I and cantilevering node J like this. Okay? All right. So then remember the next step. We make use of our differential equation. Okay. We're going to write it down. I'm going to solve it. All right. Then we're going to go to the element edges and extract the force and moment data. Okay. So assuming a prismatic beam, EI, right, d to the fourth, V, dx to the fourth, right, equals, remember, W sub y of x, right? And in this case, it becomes minus W. Boundary conditions, okay? Right? Cantilever at both ends, right? It means that V at 0 equals V at L equals 0, and the corresponding slopes are also 0. Okay, all right. Again, recall that our solution had the homogeneous counterpart, VHX, plus the particular guy, of x. Okay? The homogeneous is always the same, C1 plus C2x plus C3x squared plus C4 x cubed. Okay, nothing changed there. And V particular, right, we can actually write down by directly looking at the equation, right? So we're going to go through, right? We're going to divide through by EI as before, right? And then we're going to say, okay, V must be a function, right, such that when I take its fourth derivative with respect to x, I get this constant quantity. Right? So clearly, right, I have minus W over EI, x to the fourth, right, to get the constant upon differentiation. Okay, and what's missing is if I take 4 derivatives, I get 4 factorial, so I also need to divide by 4 factorial. 4 factorial is 24, so I get minus W over 24 EI times x to the fourth. Okay. Good. This is our particular solution. Right. Then, and again, I'm not going to go through this in great detail. I think you've done enough of those problems, right? Next is you apply boundary conditions. Okay. Determine the constants, right? C1 through C4 based on those boundary conditions. Okay. And finally, write down the solution for the vertical displacement. Okay. So if you look on page 5.3, right, you find that the vertical displacement v of x, okay, becomes minus w over 24 ei L squared x squared minus 2L x cubed plus x to the fourth. Okay, so displacement is a fourth order polynomial, right? And if you look at the figure on page 5.3, it tells you what it looks like and where the various inflection points are and so forth. Again, please refer to the reader to see that. Okay, what I want to do is focus on the extraction of forces and moments now. Right? So if we look at the moment, m of x, right, we get ei d squared v dx squared. Okay. And so if you carry out that calculation, you get the following expression, minus w over 12, right, L squared, minus 6 Lx plus 6x squared. Okay. So what do you notice first, right, is that you have a quadratic distribution of the moment. It's distributed quadratically. All right. So this has implications as to what you're going to get when you do element state determination and draw the moment diagrams. Okay, so influences, impacts, bending moment diagrams. Okay, as you will see when we go through a comprehensive example. Okay. So if you look at the notes, same page, right? 5.3, not 5.6, 5.3. Okay. What you find, right, is the moment is plotted as follows. This is x, right? And we get our inflation points. Inflation points, inflection points. I guess I'm thinking about the economy now. And you have a quadratic function that looks like this. Shoop. And it goes to the element edges. Okay, this is I. This is J. Right. The value here is minus W L squared over 12 minus W L squared over 12, okay? And at the apex, this guy reaches the value of W L squared over 24. The bending moment here is negative, okay, meaning creating negative curvature, right? Your bar seems to be concave. Then you have a region of positive curvature when the bar is convex, okay, and then becomes concave again. Okay. So this is a distribution of the bending moment. Okay. Next is the shear force. Right. V of x, recall we take a derivative ddx of m of x. Okay. Right. We'll look at the expression for m that we derived. Okay, this guy here. And from a quadratic, we'll go to a linear function. W over 2, L minus 2x. Okay. Right. And so now, if you plot it, this is your I, this is your J. It's a linear function. Right, so the shear force goes to 0 in the middle. Okay. Follows a linear profile like this, and reaches the value of WL over 2 here, and minus WL over 2 there. Okay. Good. Okay. And so now we use m of x and v of x, right, to extract nodal forces and moments to populate f prime f vector directly. Okay. So let's write it down. And this ends up being equation 5.3. Okay. So f prime f equals 2. So we just need to go and visit the nodes I and j and see what's happening, right? So first, nothing is going on in the horizontal direction, right? So the resulting forces are 0 in the first slot and 0 in the fourth slot. Okay, let me write this down. Okay, now let's collect the horizontal forces, vertical forces, right? So unit outward normal points this way, unit outward normal points that way, right? -1 here equals to +1, okay? So then when I get the value at the node I, right, I go take the -1, multiply by WL over 2. And get minus WL over 2 here. And I get minus WL over 2 there. Okay. And again, this is not a surprising result, right? You're applying the load of W, right? Force per unit length uniformly over the element, right? And so that load goes, right, and distributes half of it to, right? 1/2 goes to the first node and 1/2 of it goes to the second node. So exactly the same situation as you see with the truss element and the axial loads. Okay. Now let's go back and look at the moments. Okay. We go to this edge here, right? You see that the moment that's created is negative, right? Because the beam develops a negative curvature, okay? So the value is minus WL squared over 12, right? We'll go to the right side, right? It's the same thing. And the moment that develops is negative, okay? As the beam develops negative curvature. And so we populate the force vector accordingly. Minus Right, so again, let me go back. Okay. So in order to produce negative curvature here, right, at the location I need to apply the moment that is what? Counterclockwise, right? In order to produce the negative curvature, right? Clockwise, okay? So clockwise means negative. Right? I go here, right? In order to produce the negative curvature, right, I need to apply a moment that's counterclockwise. Okay, and the counterclockwise is positive. Okay, it's a little tricky, but once you go through it once or twice, right, it becomes more clear. And so as a result, the force here is WL squared over 12, the bending moment, and here is WL squared over 12. Okay, so basically these are the equivalent nodal forces and moments that produce a deformation corresponding to the applied uniformly distributed load. Okay, so what happens next, right? Then you have, for every element, call it element E, right? You have the forces, right? Then you go from the local to the global coordinate system, right? So the prime disappears for that element, right? Then that element will contribute remember, right, to P0. Right? And then P0, in turn, will contribute at the structural level, right, by modifying the right-hand side, like this. Okay, and again, we'll go through the details of that as we work on the corresponding example. Okay. So let me switch gears a little bit, okay, and give you an example of another distributed load that's often used in practice. And this load corresponds to the temperature case. Okay. Okay. 1 second, there we go. Okay, so I want you all to go to page 526. Right, that covers differential temperatures. Okay, and here I like this part because it's very clever. It's a clever way of trying to understand, how much bending you're inducing, right, in the in your element when you apply temperature differential. Okay. So again, what's the idea here? Okay. So we're going to take our bar, okay, and could be any cross section, right? So let's say this is a medial axis. Okay, it doesn't have to be halfway. between the top and the bottom surfaces. I'm going to put this guy on a pin. I'm going to put this guy on a roller like this, right? Okay. Then, let's look at the cross section. Ooh, ooh. Okay. Let's look at the cross section. Let's go to the next page. I can write as big as I like on this thing. Okay. So supposedly it's it's a T-beam. Doesn't have to be, but okay. So then the medial axis would be somewhere here. Right? This size will be h. Okay. And so then what we'll do is we'll apply some delta T1 at the top, okay, and delta T2 on the bottom. Okay. Delta T1, delta T2 would be applied temperature differential. Okay. So this is, again, think about a large structure and a large beam. The top side is, for example, exposed to the sun, and the bottom side is something that's exposed to the interior of a building or some other structure. And certainly, in that case, one can think of delta T2 as being, let's say, smaller than delta T1. Okay? So the whole structure is not heated up uniformly, but you assume that there's some temperature gradient. Okay? So let's take a look at that gradient. We'll have the T-beam like this. Okay? This is our, okay. We assume that the top is exposed to delta T1. The bottom is exposed to delta T2. I mean, again, I'm writing delta T2 less than delta T1, but it doesn't have to be that way, right? Delta T2 could be larger, and so forth. Right, but the key is that we're going to assume a linear distribution of the temperature, okay? And so wherever the central axis happens to be located, there I'm going to apply delta T central, okay? Okay, and then we're going to define two more quantities. Delta T top is going to be delta T1, right, minus delta T central, and delta T bottom is going to delta T2 minus delta T central, okay? So delta T top and delta T bottom become the relative, temperature differential relative to how much temperature difference the structure sees in terms of delta T central. Okay? Good. Right. So now, if you think of the our element here, okay, this guy's on a roll on a pin. I have an eraser. This guy's on a roller. Okay. This is medial axis, right? Central axis. Okay. Application of delta T central, right, results in the movement, right? Supposedly it's possible, positive, right? Then the bar would move to the right. Okay. Application of delta T to the top and to the bottom could result in and the development of curvature. Okay, so you may end up in a situation like this. Okay, where this displacement, okay, remember, I'm going to call it delta sub t, okay, was computed as what? Alpha, right? Coefficient of thermal expansion. Temperature differential, but which one? We take the central, okay, the centroid, and we multiply by the initial length. Okay? So the bar will elongate, but this guy can also bend. Okay? And so what's going to happen, right, is going to develop some angles here. Okay? So let's look at that in a little bit more detail. Okay? So let's set up. Let's take a differential element of the bar. Okay? And we assume, okay, that originally this guy was straight, right? Dx, dx, okay? And then the application of the temporal differential gave me something that looks like this. Okay? Okay, of course, everything is exaggerated, right? But I'm going to assume, right, locally I'm developing a curvature, and that curvature is constant. Okay? So this is, again, my central. And let me assume this is not the beam centroid, right, but truly something that is h over 2. H over 2. Okay, it doesn't matter so much. All right, and so what happens is if the bar develops local curvature like this, okay, I can always go, right, and find where these lines intersect. Okay? And then this becomes rho, right, the radius of curvature. Okay? Now, I can also compute this length. I drop the okay, this becomes rho minus h over 2, and this becomes rho plus h over 2. Okay? So let me draw the picture a bit more clear. Okay. I have this piece. Okay. H over 2, right? This becomes d theta. Change in angle. Okay. Now, this guy, okay, used to be size dx, okay, but now, right, the new size is going to be dx plus dx, right, alpha times delta t bottom. Okay? This is the new length. The original, right, plus by how much it deformed. So you take the temperature difference, you multiply by coefficient of thermal expansion, you multiply by original size. That's what you get. Okay? This guy, the new length, is dx plus, by analogy, right, original size, alpha times delta t top. Okay. Good. And so now I can write down two relationships. Okay, if I take the change in angle, d theta, okay, and I multiply it by rho plus h over 2, okay, which is this length here, right? So d theta times rho plus h over 2, right, will give me this length. So I get dx plus dx alpha delta t bottom. Okay. Now if I go here, this is rho minus h over 2, right? Then if I take rho minus h over 2, but multiply, this is the key, by the same change in angle, okay, I get this length, which is dx plus dx alpha delta t top. Okay. So then what can I do, right? I can then take this guy, okay, and subtract from it this guy, right? So I get d theta h over 2 minus d theta times minus h over 2 equals 2, right? Dx is going to go kill dx, right? And then I can write dx alpha, and I get delta t bottom minus delta t top. Right? I can simplify the top expression here, right? I get d theta times h equals dx alpha delta t bottom minus delta t top. Okay, from where I come up with the key expression here, right? Just divide through by dx, I get d theta dx equals 2, h goes to the right side, alpha delta t bottom minus delta t top over h. Okay, so what's the significance of this relationship? So the degree to which the angle, right, changes. So if I go from, right, so locally I develop some curvature, okay, then I go from there to there, right? The degree to which that angle changes, right, depends on the quantity that I just derived, okay? The difference between top and bottom temperature, right, coefficient of thermal expansion, and the thickness, h. Good, okay. So then, with that in mind, right, okay, imagine right, imagine the bar is now deformed like this, the whole thing, okay. This was our delta, so not delta, this was our, let me erase this for a second. So supposedly the whole bar now, right, undergoes a deformation like this, right? This is our pin, this is our roller, okay? This quantity I'm going to call minus theta t, right? The angle that's developed due to the application of the temperature differential, right? Because of symmetry, this becomes theta t, okay? And this distance here, say, is L, okay? So then what do I have, right? If I take d theta dx, okay, right, the speed at which, the rate of change of the angle, if I integrate it from 0 to L, okay, I get theta at L, right, minus theta at 0. Okay? But theta at 0, right, is minus theta t, and theta at L is theta t. Right? So it's the same thing as theta t minus theta t equals 2 theta t. Okay? At the same time, if I take integral 0 to L d theta dx, right, then I go back and I use this expression here. Okay? This is integral 0 to L, right, alpha delta t top minus, alpha delta t bottom minus delta t top over h. Okay, nothing depends on x here, so I can take it outside the integral and get the L. And I get alpha delta t bottom minus delta t top L over h. Okay, and so now, right, I've come up with a relationship. So now clearly, right, I have two expressions for this integral. Okay, from where I conclude that theta t equals to alpha delta t bottom minus delta t top. Okay, this is not L, this is H. Over 2H, okay, times L. Good. Okay. Okay. Right. So now I can finally model f prime f, okay, in the basic system. Right? So what was the idea? Right? F prime f was obtained by taking the basic stiffness, right, and multiplying by what? By the negative of the basic displacement. Delta over bar prime 0. Right? This is basic stiffness. And this guy is the basic displacement. Okay? For the beam column, basic stiffness was what? 4EI over L, right? 2EI over L, 2EI over L, 4EI over L, 0, 0, 0, 0, EA over L. Okay, now what about the basic displacement? All right, let's look back. Okay. Rotation at this node is minus theta t. Rotation at that node is theta t. Okay. And then we had a displacement that was computed by taking alpha, right, delta t central, right, times the original length. Okay. So then f prime f over bar equals to the basic stiffness times the negative of this guy, right? Which is alpha L delta T bottom minus delta T top over 2H minus alpha L delta T bottom minus delta T top over 2H minus alpha delta T central times L. Okay. So, to be more consistent now with the notes, okay, let me flip the sign, right? Let me go and change the bottom and top. Put a negative. Put a positive here. And replace it with delta T top minus delta T bottom, okay? And now we get exactly the expression right given in right, this is our delta prime 0, right? And if you look at the expression in equation 5.7, you get the same thing. Okay, so my derivation was a little bit different. Okay, and so the next steps, okay, you just basically do the multiplication, okay, and you end up seeing the following vector minus alpha E I delta T top minus delta T bottom over H alpha EI delta T top minus delta T bottom over H, and you get minus E A alpha delta T central, okay? And then we can compute f prime f, okay, in a local system. Okay. And remember, okay, this was gamma transpose, right, RBM times f over bar prime f, right, the connection between the basic and the local coordinate system, and then you end up with a vector that looks like this: EA alpha delta T central in the X location, right? Nothing in the Y location, right? So no vertical forces, right? Very important, right? No vertical forces are generated by temperature difference, okay? Then you get minus alpha EI, okay, delta T top minus delta T bottom, all that divided by H, okay? Then you get minus EA alpha delta T central, right, at the J node. Then you get 0, no vertical forces, and you get alpha E I delta T top minus delta T bottom over H. Okay, and so now this vector goes into F, F, and then it goes into PF0, and then it goes to the structure. U equals P minus PF0. Okay. All right. Let me stop here, and the next lecture will actually cover the example that involves the distributed load, and I think I'll just leave you the temperature example to do on your own.